All right, we are back to some theory. If you look at our sheet right now, if hopefully you're doing these in order, right? You're looking at the videos in order. We have just finished problem number 4, and I know you're all excited. Problem number 5, we're almost done. Well, we are. We're almost there, but we have to do some talk the talk before we can walk the walk. And that means we have to do some content. Right now, we're down to, if you're a person who has your topics list out, we're down in here. So we have to do this stuff here, and a lot of this is content. So I'm going to go through these terms here with you. Okay. On the board behind me and or in front of you, you can clearly see that I have drawn what looks like kind of like a graph. And I've graphed what's called energy versus time. So not Tom versus time. Okay, that would be, TB12, good old Tom Brady who plays for the Patriots. We're going to like to see him no, he doesn't. Doesn't anymore. Sorry. I know, too soon. Okay. Where was I? Okay, so let's say that you have 2 reactants. We'll call them reactant A and reactant B. Okay. These are going to react with each other and form some compound. Maybe they'll form compound AB, maybe they'll form new things, CD, whatever, forming some product. Okay, so if they form a product, here's what happens. There's a certain energy level that these 2 reactants bring to the game, they bring to the table. Then they react. Now, up here, as they're reacting, they are going together. Now, this is called collision theory, and I've mentioned it before, that in order for something to react with something else, one, they have to collide. And there has to be a certain amount of energy in their collision. And they have to be oriented in the right way for them to actually do something. So most collisions do not result in a reaction. But if you have a lot of high temperature and they're moving very fast, there's more collisions per unit of time, they're more likely to react. Now, when they do react, when they finally have the right speed and they're going at the right orientation, they go, and they go, yes, and they make a connection, that's the AB. That's called the activated complex. So when the 2 reactants come together to form this brief, what's called activated complex, it doesn't last very long. Because remember, what we have is A and B going together to form something. I was going to say, let's say this is a compound and a compound, and maybe it's a double displacement reaction, and they form 2 new compounds. Okay? So maybe A and B are going to form C and D. But they can't form C and D until after the AB get together and make it not A plus B, but make it AB. That's the activated complex. It doesn't last very long. It's a very short period of time, and then they make the product. Now, the product that they're going to make, in my example, is C plus D. Okay. Notice something. This is energy. As the reaction's taking place, the energy skyrockets here. This energy needs to go into the reaction to get the reaction to happen. That's called the activation energy. So the activation energy is the amount of energy that you need to go into the reaction to have these 2 do their thing and make the magic. So that activation energy, sometimes it's very high, sometimes it's not. Some reactions happen very quickly with very little prodding along. In the movies, like the old West movies, they used to use nitroglycerin, and somebody would be walking around with a little bottle of nitroglycerin. Careful, because if they sneeze, achoo! Didn't take very much energy. That little sneeze motion was enough to boom, cause the reaction to happen. Okay? Movies. So good. But this activation energy can be an awful lot. Sometimes it really takes a real kick in the pants for it to happen. And, you've got to give it a lot of energy. We did a lab in my chemistry 1s. Some of you are in my chemistry 1s. We did a reaction with magnesium oxide. And the reaction happens. It does happen. We were kind of speeding it up. We gave it a little bit of a kick in the butt by firing it up and making that reaction happen. So that activation energy is how much energy it takes to get these two to do the thing. Now, after they do their thing, check this out. The energy is down here. We started here with energy, we ended here with energy. That's called an exothermic reaction. This would be exothermic. How come it's exothermic? Because we have a change in energy, and we started with more than we ended, so we must have given off energy. Energy must have left, exit, exothermic. So we lost energy because it left, exited. That's an exothermic reaction. And we will get into exo and endothermic reactions in detail toward a little bit later in the course, toward the end of the course, when we go through thermodynamics. All right? So stay tuned. But for now, know that this energy is now less than we began. We've lost energy. It's exothermic. Endothermic, what would that look like? If it was an endothermic reaction, I wanted that to be the black marker. Stay consistent. It would be like this. So we start with this energy, we end with this energy. So the energy's gone up, energy's gone into, entered the system, endothermic. That would indicate an endothermic reaction. The vast majority of reactions are exothermic. Because when you have a reaction, it brings the energy level down and calms everything down. You're like, ah, and then a reaction happens, like, phew, okay. Mellow. Nature likes mellow. Yes, it does. Okay, exothermic. Let's see, what else? The activated complex, that's the thing that briefly goes together. They do their thing. They make the products. This is the reactants. These are the products. The difference in energy tells you it's endo or exothermic. Let me check the sheet. Sometimes the sheet is not necessarily for your well-being, but it's for mine to make sure that I cover everything. I got to remember everything. Activated complex. Oh, the Arrhenius equation we will go through. Actually, the Arrhenius equation, well, that makes sense. That must be the last problem, and it is. The Arrhenius equation is used to determine what that activation energy has to be. What is it in a reaction? And we'll use that in the last problem, problem 5, to calculate that. Let's see, what else is on here? Reaction mechanisms. Okay. So, and you also enter reaction mechanisms, elementary steps. Molecularity of a reaction, molecularity, and then the rate determining step. Okay. So over here, can you see that? You can see that, right? I put a generic reaction taking place. The vast majority of the time, reactions take place in 2 steps, sometimes 3 steps, not 1 step. What you see, and what you've seen on our sheet of problems that we've been doing, are equations for reactions. There, here. All these equations for reactions, the last one we haven't done yet, show you a reaction, and you just go, oh, okay, just 1 step. All reactions are 1 step. No, the vast majority are not 1 step. What you are seeing is the final step. You're seeing the bottom line overall equation. You're not seeing the steps to get there. You just see there. Okay, now let me show you a generic, so I just put letters up here, not an actual equation. We could, but let's put some generic letters up here. This would be step 1. Step 1, step 2. This represents the overall reaction. And this is what you're going to see. You're just going to see an overall reaction when it comes to doing these problems. Because for the most of the time, we don't care about the elementary steps. Those are called. They're called the elementary steps. Step 1 says A plus B makes AB. Okay, and that would be an activated complex. Then AB reacts with some other chemical and makes ABC, which would be actually my example, a second activated complex. And then from ABC, we end up getting, so this is a 2-step reaction to give me an overall reaction. Now, how did I get this overall reaction from those 2 reactions? Reactions are equations, they really are. These arrows with our reactions represent equal marks. So if we have this happening, making AB, then AB combines with C to make ABC. And then what we do is, whenever you have the same thing on either side in an equation, what happens to it? Like if I have an X on this side and an X over on this side of an equation, it cancels. They cancel. And this is all happening at the same time, making this overall reaction. So if I have something on the left of one of these elementary steps and the same thing on the right, they cancel. Let's see. The AB appeared as step 1, the AB appeared in step 2. Those are on opposite sides, all right, the opposite sides of the equations. They will cancel each other out. Because remember, this stuff is all happening at the same time. We just separated them out for organizational purposes. They cancel. What are you left with? On this side, I have an A and a B and a C. Crikey. On this side, I have an A, B, C. Double crikey. So we end up getting the overall reaction from the two partial or elementary steps in that reaction. Okay? And this is what you're going to see. You're not going to see these steps. Now, here's the thing. This is actually what I wanted, my important point about this elementary step stuff. One of these reactions aren't going to happen at the same rate. I mean, yeah, what are the odds that both reactions would, because they are different, would happen, these two elementary steps, what are the odds that both of them are going to happen at the exact same rate? No, they're not going to. So somebody is going to be faster than somebody else. Maybe reaction A is faster than reaction B. The slower reaction is called the rate determining step. The slower reaction is called the rate determining step. Let me give you two analogies to that. A chain is only as strong as its weakest link. So if you have a weak link, that determines how strong the chain is. If you have a slower reaction, that determines how fast this reaction is going to happen. One other example. You ever drive out toward Keene, New Hampshire from like 111? No, 102? I don't remember. It's one of those, I think. I think it's 102. Yeah, I think so. Anyways, point is, you're driving out toward Keene. Okay, that's just it's 2 lanes. One lane, 1 lane. And if you get stuck behind Grandma going on a Sunday drive on a Monday afternoon at 5 o'clock, okay, you know how frustrating that is. You can't pass. So Grandma determines the rate of all the traffic. Why? Because Grandma's moving the slowest. The rate determining Grandma determines how fast everybody moves. It's the same thing here. The rate determining step, the slower one, determines how fast the overall reaction takes place. In fact, if we knew the rate of the rate determining step, all that stuff that we were doing earlier, problems 1, 2, and 3, we wouldn't have to do any of it. You just have to know the rate of this rate determining step, then you know the reaction rate. Life isn't always that simple. Anyways, I wanted to mention that. You got rate determining step. Oh, and one other thing. Sometimes the equations that you have, if you look at your sheet here, the molecularity of the reaction, uni, bi, or term, what that means is how many reactants you have. If you have one reactant, remember the reaction that we just did, the one with the phosphine, was that the last one? No, that was the nitrogen dioxide, but the nitrogen dioxide, problem 4 and problem 3, had one reactant. Okay, that would be unimolecular. Okay, you have one reactant. Bi would be, you have 2 reactants, and term would be 3 reactants. So on here, this elementary step is bimolecular. This is bimolecular, 2 things. This overall reaction would be, you can call it trimolecular, but it's called termolecular. All right, TER, termolecular, that means 3 as well. Those are actually kind of rare. You usually don't get those. Usually it's, most of your reactions are bi. And the second would be your uni, and then this would be the least common. Okay, hang on, we're almost done. We're almost done with the content here. So we got rate determining step, molecularity, did that, elementary step, reaction mechanisms. Okay, we'll go back to the equation for problem 5. And then last but not least, catalyst. Catalyst, okay? What is a catalyst? Oh, you've heard of catalyst. It's when a cow is standing on a hillside. Catalyst. A cow is on a hill, so it's listing. Okay, no, Billy, no, not that catalyst. A catalyst is something that, what? I mean, most people would say speeds up a reaction, right? And that's absolutely true. The question is how? How does a catalyst speed up a reaction? And biological catalysts are called enzymes. Yes, enzymes are biological catalysts. So a catalyst, an enzyme is a catalyst, but not all catalysts are enzymes. Okay, they are chemical catalysts. Platinum is a very good catalyst that's used in a lot of reactions to speed up a reaction. So what is a catalyst? What does it do? Okay, a catalyst is something that will speed up the reaction but not get involved in the reaction. It's not a reactant and it's not a product. It doesn't appear on either side of the reaction. Usually you write your catalyst on the arrow. A plus B makes C. And your catalyst will go here just to show that we're speeding up the rate of this by using a catalyst, but it's not either A, B, or C. If it is, if the catalyst is in the same state, like for example, if this is a gas and your catalyst is a gas, then that would be a homogeneous catalyst. If it's in a different state, which it usually is, a lot of your catalysts in chemistry are solids, and then we're dealing with liquids or gases quite often, and then we end up getting a heterogeneous catalyst because it's in a different state than the reactants. A very important catalyst occurs when we get, oh geez, we're getting low battery, get out of there. A very important catalyst occurs, which actually there's a reaction that makes ammonia. You get nitrogen and hydrogen makes ammonia. It's huge. Ammonia is hugely important in industry. And it was important a long time ago, and the Haber process is the process of speeding up the reaction, because those two things will react with each other, nitrogen and hydrogen, but they do it at a very slow rate, not enough to make an industrial amount of ammonia that you need. So somebody was really smart, and they figured out how to speed that process up by using a catalyst. Okay, anyway, so how does a catalyst do its job? Right there, right there. It does this. A catalyst, remember this, okay, I'm warning you. A catalyst will lower the activation energy. It brings the activation energy down, so not as much energy has to go into getting this reaction to kick off. It's easier to get the reaction to happen, so it'll happen at a faster rate. So a catalyst lowers activation energy. The catalyst does not get involved in the reaction. The catalyst before and after the reaction is still the same. You can reuse your catalyst over and over again, just like biological enzymes can be used over and over again. Until you get older, though, as you get older, you become lactose intolerant because your lactase, that's the enzyme that breaks down that sugar, sometimes can kind of get old and go away. Okay, so I think that wraps up all the terms that we have. Now that would take us to the end of the first unit after we do problem 5. Don't go away until we do problem 5 on our sheet. That's all the material though, all the content in the unit 1. Okay, one more problem and we're done with unit 1, and you're going to be ready for the test and excited.